let me run through the science of straws. I love this little kid, adorable. I imagine this is like what I was like when I was a kid, just blowing stuff up all the time in the name of science. So here's what we've been working on. So over the last sort of 2.5, 3 years, we've been working on a multi-phased experimental approach, measuring the capabilities of different straws. And so we started by building a mathematical model. And this mathematical model looked at the relationship between the length and the diameter of straws, and then change in length and diameter, or change in diameter across the length of a straw. So it kind of looked at these variables as well as material property. So if the straw is stainless steel, paper, silicon, all that kind of stuff. And it took this and we plumbed in known physics. So things like atmospheric pressure, air density, things like fluid viscosity, so how viscous the airflow is. We looked at gravity to see if there's any change, because I'm a super nerd, to see if there's any change for things like being on Mars with slightly different gravity, because why not? And then what we did is we validated this data that we got out of this mathematical model against the literature. And so there's mathematical models that already exist in the literature, but they're slightly different to ours in that they only account for fixed diameter and fixed length straws. So your regular straw that you'd pick up off the shelf of a supermarket. Whereas our model looked kind of any straw, regardless of fixed length and fixed diameter, you could change diameter across length and change all the variables about your straw and generate the results. The trouble with that, though, is this is kind of like a photograph. It's momentary. It's a single snapshot of what your straw is capable of. But for singing, we need to know what the straw does across time, because we have the momentary input. So we have the start of the airflow, and then it moves through, and then it stabilizes the airflow and the air pressure in the straw. And then as we finish that airstream, other stuff happens. And so we wanted to account for that. And so that's why we moved into something called CFD, computational fluid dynamic simulations. And this is basically like video. So we're kind of animating this pressure and acoustic energy as it moves through the device. All we really did here is we just said, I want the input to be down here, I want the output to be down here, and I want my air to move through at a given flow rate. And then we let the system take all of those properties of physics that we looked at before and integrate them into this model and generate us a pretty cool animation of what's going on. And so the animation, I hope it plays for everybody here. But the animation is looking at pressure change in the straw. So you can see at the input, we're red. And as we move through the straw, we kind of move into the blues. And so that means as we move through the straw in terms of pressure, we're decreasing the pressure between the inlet and the outlet. And that's, of course, due to how we've engineered ours in that we've changed the size across the length of the tube. And based on what we know about the theory of change in diameter across length, we change the airspeed, and in changing airspeed, we change the pressure. So if you want to know kind of more about the nerdy sciencey stuff in detail, I have a sort of 4-hour streaming course that looks into all of this. But for now, I think the important thing to know is we did the measurements, we did the data, and again, we have really good agreement with the literature, which is cool. And then I noticed another problem. Both of these mathematical versions are perfect world scenarios. They don't account for variability in the real world. For instance, if we have a window open and there's a little bit of a breeze and that changes the pressure in the room that you're trying to sing through your straw into, or if you have a fan on, or if you're working in a company and you've got, maybe 30 people all doing different vocal exercises or blowing through straws and changing the pressure in the room. So I really wanted to account for that. And so we built, we 3D printed, to design and 3D printed a hardware test rig, built some rigging with different sensors on it, and we could put straws inside and we could change the environment, change all sorts of physical parameters. And again, we can test and validate. And what's really, really cool is the result of these 3 experiments allows us to do things like this. we can map out exactly how much resistance any configuration of straw can offer. So in this graphic here, this is our SOVT straw, but in this graphic here, this is kind of any other straw. So I'll talk you through both real quick, because this helps us really understand the honing technique. So with regards to our SOVT straw, as we move from the left to the right, we decrease in resistance. So we lower the resistance as we move from left to right. And again, resistance is like weights in a gym. So the higher the resistance, the more weights you have, the harder the task. So this is really cool because now you can just put your straw in the pictured configuration and you know if it's high resistance or low resistance, which is great. And what we do is when we're honing, we are just testing, let's say, configuration 1A with our 2 exercises that we looked at before with the breathing drills and or the voice drills and the pitch glides. And then once we've tested that and noticed how that feels, we'll maybe move to 4C and test that one. So we've got high resistance, low resistance. And then we might work inwards, or we might work down, or we might work up. And we'll just play about with the way we work until we settle on a configuration that feels comfortable and balanced and feels really good for you. So let me explain what this means for regular straws, because I know not everybody has an SOVT straw, and that's absolutely fine. So the diamonds, the green diamonds, are the fixed configurations of our SOVT straw. So those are the pictured ones that we have here. And then the green line is all of the variability in between. So this is all of like the change. So if you go from this long and then change it like a millimeter or a millimeter or a millimeter. So it's all of that variability in between that would just be impossible for us to display to you in a reasonable way without having just masses of data on a screen. And then when we look at the kind of orange line, this is a 5 centimeter long stainless steel straw. Then we have in the red a 10 centimeter long stainless steel straw. And then in blue, 20 centimeter long stainless steel straw. And then across here, we have just diameter. So 3 millimeter diameter, 4 millimeter, 6, 9, and 10. And again, I don't want this to be scary. I just want you to kind of use one of the best human skills, and that's pattern recognition. It's super easy. This stuff is bigger than this stuff, which means this stuff has more resistance than this stuff. Now, we can see some other really interesting traits here in that the different lengths within a diameter condition, there's not much change in resistance. But when we change diameter even by 1 millimeter, we get a huge change in resistance. So when we're looking at different straws, you'll get a huge change by changing the diameter, bigger or smaller. And you'll get smaller incremental changes when we change length, again, longer or shorter. So let's take the 3 millimeter diameter, 10 centimeters long straw. That's about 15 what we call CmH2O, centimeters of water of pressure. I'll explain what that is in just a second. And then if we look at the equivalent in a 10 millimeter diameter straw, we're looking at like, 0.1 less than. So this has big resistance, this has little resistance. And that's really important, again, for that honing. We want to test with high resistance, then low resistance, and high, then low, then high, then low. And we just work our way until we find something that feels comfortable and balanced across both of those exercises. So here's some things to remember. CmH2O, centimeters of water of pressure, is exactly that. It's a fancy way of us saying pressure. It's an alternative unit to things like PSI, pounds per square inch, or pascals. You can easily convert the two. It's just for some reason in the vocology domain and the respiratory medical services use CmH2O as their standard. So that's what we adopt. So again, you want to think of it like weights on a training machine in a gym. The bigger the number, the harder the task. That's the kind of general rule. And we change how hard it is depending on the diameter or the length. So smaller diameter, harder task, longer length, harder task. Using your straw in water also changes the resistance. And now we have this really convenient thing now because it's measured in something called CmH2O, centimeters of water. And then we can put the straw in water to change the resistance even more. And what we want to do then is every centimeter of water that we put our straw into, we add that onto the resistance value natively of your straw, which is why we've gone and done this graph. So let's again take the instance of this 15 CmH2O straw. So that's 10 centimeters long, 3 millimeter diameter, so 15 CmH2O. If you put that into a 10 centimeter depth of water, that entire configuration becomes 20 CmH2O. So you add the resistance the straw is capable of by itself onto whatever depth of water you put it into. So that's slightly problematic, because if we're really comfortable using a 3 millimeter diameter straw outside of water, and we want to match that resistance inside of water, we have to do a little bit of playing about, maybe changing the diameter. If we change it down to 4 millimeters, and we've got a 5 centimeter long, so that's 5 CmH2O, we know now that if we put that configuration in 10 centimeters depth of water, we'll match the configuration that we had before that was comfortable. So it's a little bit of playing about. Good news is we're working on a digital platform that takes my math and our simulations, and it presents it in a format that you can interact with and play about with in order to calculate an infinite variable of straws, an infinite number of straws, see what the resistance is, and get some really useful tips about what that does for different voice types and for your voice. So we're going to be launching that probably around October time, maybe November time. So keep an eye out for it. It's going to be fun to play about with. And now I just want to quickly share some of the science in the press. So there's been some really awesome science that's come out over the last few years about straw phonation. I'm not going to read everything here because it's also on the website, but I just wanted to share that a lot of good people are doing a lot of cool science on this topic. There's really good data to suggest how positive the effects of straw phonation is on vocal economy and vocal efficiency, both in self-assessed conditions and also in kind of more sort of empirical, looking at actual pressure and resistance of people in different conditions. So this is a really cool thing. It's a really cool emerging science that has started to grow over the last few years. I'm really happy to be contributing to this field because it's pretty fun. So I just thought I'd share that with you. So now what we want to do then is we want to explore, experiment, and adjust. So exactly the same two drills that we've just done before, but again, we just want to rotate between different straw conditions to find something that works for you. So you'd start with high resistance, low resistance, work your way up, down, or in. So those are some things that you can play about with. These are the exercises, again, for your explore, experiment, and adjust.